Let me introduce myself a little bit. Jim Sweeney, Texas A&M University. I work for the Riverside Energy Efficiency Lab. We're a mechanical testing laboratory, but I'm also involved in building energy and water management. So I'm going to talk to you about my PhD project that I've been working on, and it was the overarching context of the project was a life cycle analysis of a home that was built in 2009. Excuse me. So for this, I'm going to specifically talk to you all about the residential energy component. This house, just to give you all a quick little rundown on the house, it's a very large home in the medical center area. The individual was trying to achieve the most efficient home he could with a large footprint. I know that sounds perhaps contradictory, but this is a pretty common type of home in this type of environment. So the idea is to make it as efficient, water conservation and whatnot, and design an optimal building envelope to minimize the energy utilized for heating and cooling. Obviously in Houston, Texas, it's primarily cooling. And in order to offset operational energy, renewable energy components were added. This house, on a side note, it also had a rainwater harvesting, and it was awarded a LEED Platinum designation for homes last year. So this house is located, like I said, near the medical center in Houston, so it's fairly close to the coast. It has a pretty high irradiance. There's some general location parameters, and also the location of the systems. Apologies for not putting the cardinal directions on that particular image, but the photovoltaic system is basically facing south. The house is pretty much oriented north-south at its longest point. So you can see the solar thermal system is pretty much facing due west. So what I'm going to present to you all is my experience with using SAM to evaluate these systems and compare it with some measure data that I took at the site and evaluate the system over basically a 30-year life cycle. So here's some details about the solar photovoltaic system. It was a grid-tied system. It had 20 170-watt solar panels. This is obviously an older system. It's from it was installed in 2009. But even then, some of the systems that were put in place were a little bit, they weren't brand new, I guess you could say, from the installer. The total size was 3.5 kilowatt, estimated to produce. The solar installer used PV watts, and he estimated it at 46 per year. And like I said before, it's installed due south and a 40-degree tilt. The panels are sitting basically on top of the garage area. There's the microinverter specifications. The system had basically on-phase MP175 microinverters on each of the panels. Here's a systems overview of the solar hot water system. Some of the details. This is an Interworks. I'm sure some of you may or may not be familiar with Interworks, being in the renewable energy field. This is a single plate, 4x8 flat plate collector with an energy transfer core connected on the left. You can see the picture of it connected to the hot water heater. The system, you can see a diagram towards the bottom right. The system basically preheated a on-demand heater, a super efficient gas heater, to bring up the temperature when it needed. So basically what I did was I took some field estimates from 2012 and 2013 and ran SAM with the best estimates of the site conditions. And I took I used an inclinometer to make sure that the elevations were correct, and performed an annual simulation. And then this basically shows 2012 and 2013 compared to the simulation data. And for the purposes of the life cycle approximation in the context of the whole building, this was a reasonable expectation. The only major concern I wanted to see was, how the radiation may vary. Now, this particular model I didn't identify earlier did not include any shading. You could see there was a little bit of a tree off to the left for the solar photovoltaic system. This model doesn't have any of that, and it does. The TMY estimation does underpredict that, and it's probably for that case, and maybe even the fact that there was probably some soiling at this point since it had been there for a couple of years. But this is the model and an approximation at this point. So I wanted to look at also look at the variation over for the solar radiation to see if there was any significant variation within the past within the NSRDB data set. So I used SAM's very powerful tools to estimate the P50 and the P90 probability against the TMI estimation. And if any of you have used these tools, if you have not used these tools, I would strongly suggest looking at them, because it very quickly gives you an idea of the variation in radiation for the system and how the models are predicting versus your model or your measured data for the short term that you're looking at. And in this particular case, it's no surprise, even though there is a significant amount of cloud cover, the estimates are pretty consistent across the board, with a minimal amount of deviation for this point. So you can see the annual energy for this particular system was close actually to the PV watts estimate. So now I'm going to move on in the instance of time. This is the solar hot water system predictions in the same type of arrangement that we saw with the photovoltaic system. In this case, the hot water system estimates the measured estimates were based on the collector output temperature and some estimates on the efficiency transfers within the energy pack and to the losses in the tank. And also the hot water was estimated based on ASHRAE 90.2 hot water demand estimates from the house. I didn't have hot water demand data, so I used this particular system to estimate the annual savings. So these predictions were a little less accurate in some cases for the month, but as been stated before, the month uncertainties can be quite high, and even the annual uncertainty has been reported, from even higher than 10%, depending on the radiation being used. And again, here is I explored this utility in SAM to assure me that that the output, basically that everything was cooperating and running correctly. So here are some of the model costs that I assumed. The initial costs were quite high compared to today's costs, but not unreasonable. This is like around $7 per watt or something like that back in 2009. So, and the solar hot water system it's also fairly expensive considering the amount of energy gained in this particular market, but that is what it is and what the customer paid for it. And the lifetime cost I estimated based on a reasonable amount of maintenance with cleaning, and this is difficult to estimate basically their lifetime replacement cost, but I assumed a few panel replacements and the energy pack replacement in the solar hot water system. So about $2,400 for lifetime cost replacement for solar photovoltaic, and about $1,800 for the solar hot water. So a life cycle performance looked like this approximately for each individual system. As you may or may not know, the solar hot water system within the SAM model, the default is electric heating supplement for auxiliary heat. So I also ran the SAM macro to estimate what it would be with natural gas heating with the efficient heater, and as you can see, the production increases a little bit. and there's the life cycle estimates with basically for both systems a 0.5% degradation. So looking at this from a life cycle point of view, also utilizing SAM's utilities for calculating net present value and the levelized cost of energy, we can see that the the payback for the probabilistic payback for this particular system and this economic system is not great from a net present value, but as I stated before, that wasn't necessarily the driving force behind this. This house was designed to try to minimize its impact in the environment, but at such a large house and these kind of types of constraints with Texas, it's challenging, at least at that particular time. And utilize the levelized cost of energy as well as an index to look at how the cost will impact it, and I'll get to that in a second. But the price of electricity in Texas is also quite low. It ranges from 8 cents to 10 cents. This model utilized the 10 cents, and in Houston, that is almost a worst case scenario. So solar hot water system predictions are a lot more advantageous, primarily because of the cost to energy performance, or basically. So there's the presentation of the real levelized cost and the payback and the NPV, just the same as the solar photovoltaic presentation a moment ago. So basically, we're looking at 21 years. Seems like a long time, but in this particular situation, that's where it's at. And that present value over 30 years is, from a TMY simulation, it's about $800. So I wanted to kind of look and see how far will we have to drive down the module cost to make the LCOE approach 10 cent mark. So this is a 25% sensitivity analysis, a very simplified sensitivity analysis, 25% swing on the individual cost of the system for the TMY based estimation. This is particularly. Just as on a side note, I believe it would take almost a 67% reduction in the module cost at that price point. It was at 2009 to get it down to 10 cents. So that's about all I have. And so in concluding that, the field measurements of the solar photovoltaic and solar hot water are within reasonable limits of the model and the metering uncertainties, especially from an annual and life cycle perspective. SAM and the NSRDB combination are very useful in determining radiation impacts quickly on the performance of the system being analyzed. And obviously, life cycle performance is very sensitive to initial cost. And I did some of the sensitivity analysis that I showed you guys through just using the macros that were set up, tornado charts. But it's very helpful and very, very quick to develop those type of analysis. So that's about all I got, guys. Hope I wasn't too quick, but I had a lot to cover.
That was great. Thank you, James. If you don't mind, this is Nate Blair. I'll start off the questions. I'm curious about the sizing of the PV system for a house of that size. Do you have any information about kind of the electric load, and if there's much selling back to the grid, or maybe even how many people live in the house? Why don't we start there?
Yeah, it's a great question. I did not design the system, but yeah, the system has 4 people living in the house, which is of course a small number of people for a large house, but that's what we have. And the annual electrical consumption is like 30 to, actually no, I'm sorry, I misspoke. That's the total energy consumption. is 60, 50 kilowatt hours, 1,000 kilowatt hours, including gas. Electrical is around 30 to 40. So, these systems are barely getting around 10% on an annual basis of the whole thing. So, does that answer your question? So it's making a small dent. It's making a small dent, but it's not really changing the aggregated. It's not changing a whole lot the aggregated energy over time for the whole house. But given the cost of the system in this market, that was a reasonable starting place, I guess.
Great. And then did you take a look or try out the kind of the automatic load generator in SAM at all?
Yes, I did. And I didn't work with it too much. I can't give you any specific reasons. I was having to pull this into my simulation anyway. Like I'm using Energy Plus for the energy consumption modeling. I have actual data for that as well. Maybe I should bring it into this, but I haven't done that yet. Actually, I'm just now finishing up the Energy Plus simulation on the house. So. Right. So the larger context is, I still haven't completely jacked in. Hopefully I'm going to wrap this up in a couple of months. Hopefully, that's my plan.
Okay. Great. And do you have any idea from the homeowner if they had it to do now with prices significantly lower, if that would, change what they decided to do, perhaps add more panels or do something else?
No, absolutely, and he is an advocate of this technology, and he recognized even back then that just having this thing set up ready to be plugged into is alone worth having. Does that make sense? It's like having the equipment there. Like even if you can only afford, a couple of thousand kilowatt system, that having the extra equipment, the electrical equipment in there is worth doing because of the economic pressures that we've seen on the photovoltaic production. The Sunshot presentation that NREL produced some great information in there about all these markets.
Great, thank you.
We have a question that came in on the chat asking you to remind us what the installed capacity of the PV system was.
3.5 kW.
Excellent. And then I actually had a question that's pretty far in the weeds, so apologies for that. But I saw that on one of the slides you mentioned you used the HDKR model for transposition instead of the Perez model, which is the default in SAM. I was curious if you could speak to that a little bit or had anything to say.
Because this project is multifaceted, I've been doing a lot of different things on this project, and I remember researching that, and there was some literature that I found that indicated that was a better model in this particular instance, but I can't remember why. And maybe it was something to do with predictions were closer to measured values, but I didn't run it in both ways. Maybe the more maybe y'all's expertise could guide me in one direction or the other. I don't really have a good solid ground to stand on other than I referenced it based on some other literature.
Yeah, we've done one validation.
Is there a reason why the Perez model is the default?
We have looked a little bit at the comparison between the Perez model and the HDKR in a validation study we did a few years ago. And for the 9 systems that we looked at, there was no clear winner, I'll say. Sometimes one was better and sometimes the other was better, closer to measured data. So we are always looking for more information on what to recommend people to use. I've seen some of the literature that says, that recommends one over the other, but I've also seen conflicting literature in that, so I'm not sure that there really is a clear answer, which was why I was curious. So I would like to get other perspectives. So thank you for that.
Yeah, we have another question in the room as well. Just a short one, actually. So in your analyses, I saw that you included both the empirically defined P50 and P90 as well as the P50 and P90 from a normal distribution. I was just curious if you actually looked at the annual productions for each of the years in the P90, P50 analysis, and just curious how well it actually fit a normal distribution, or if there were just a few years where there was significantly more production as opposed to others, or less. Hello.
Okay. I was using that to look at the general annual for looking at the NSRDB data set, basically, and comparing that with the TMY. Because in my thought process, I'm doing a 30-year extrapolation, or maybe even longer, 50-year. That specific years in particular weren't my main concern. In the beginning with the measurements, that was just like a sanity check. Everything's working correctly, basically.
Mm-hmm.
Does that make sense?
Yeah, it makes sense. I was just curious. Thank you.
Mm-hmm.
Hi, my name is Nick DiOrio. I have a question here at NREL. So I'm interested in learning more about the validation study you did with the solar hot water, and if you're going to publish that, or if it's already published.
No, I plan on publishing that. So
great.
That
yeah, looking forward to seeing it.
This information will be expanded on in the forthcoming paper, actually.
Great. And then was there?
That's great because we don't have any funds to validate the solar water heating model ourselves from DOE. So, I think we would love to get a copy of that when you've got it out there.
Well, I would love to even talk to you guys further about it, if that's okay. Who are the right people to talk to? All of y'all?
I'd be happy to talk with you. My name again, Nick DiOrio. I can follow up with you.
Okay.
And then I guess one other question was did you have any specific needs in the solar hot water interface that weren't available that you could see room for improvement?
Yes, I think maybe some, without getting too specific, more detail on that, and even not to go into this too much, but there's some gross assumptions that I had to make. So I had measurements coming out of the panel, so I knew it was being delivered. So I had to make some estimates based on what was delivered to the hot water heater. So that connection there could probably be worked on, if that makes sense to everybody. You have to refer back to the graph with the systems. But.
Okay, great. Yeah, I can't promise any future work will ever be done on solar hot water, but I'd be curious and just following up with you and learning more about kind of your requirements.
Right. Yeah. Even finding uncertainty measurements and just assessments in the past and the solar hot water was very difficult, almost impossible.